So now we're going to look at the stress field in polar coordinates and take a look at the significance of K1. So we're going to start where we left off last time. Consider capital Z is equal to K1 square root 2 pi Z star. Now we're writing the strength of singularity in terms of K, stress intensity factor. And now we have Z star, the distance from the crack tip, and we know that that's equal to X star plus I Y star. But we can express this in polar coordinates as Z star is equal to R e to the I theta, where the R, well, R squared, is equal to X star squared plus Y star squared. Oops. Or if we want to go back to our coordinate system at the middle of the crack tip, x minus a, at the middle of the crack, x minus a squared plus y squared. Oops. All right, so again, let's draw our crack coordinate system. Here's our original x and y, but we're at the crack tip. So that would be my x star distance, and here off in some area would be my z star. And at a particular point z star, let me draw one way up here. This distance on this side of the triangle would be x star, and this would be my height, y. And this would be my angle theta. And we can say that the tangent of the angle theta would be equal to y over x star, or, since the distance from the origin originally of the middle of the crack to here is x, then we could say it's equal to y divided by x minus a. All right, so let's look at that function z again. Capital Z is K1 over the square root of 2 pi little z star. And since I know little z star in terms of r and theta, I can rewrite this as K1 square root of 2 pi, those are the constant terms, r to the minus 1/2 e to the minus I theta over 2, because the 2 was on the bottom. All right, now our stress field sigma x we saw was the real part of z minus y times the imaginary part of z prime. Now z prime, we said, was the straight derivative of capital Z with respect to little z, or in this case z star. Same difference for us right now. And capital Z then would be K1 over square root of 2 pi z star to the minus 1/2. So that means the derivative, capital Z prime, would be equal to minus 1/2 K1 over square root of 2 pi. We'd have z star to the minus 3/2. In terms of r and theta, then, we can rewrite this as minus 1/2 K1 over square root of 2 pi r to the minus 3/2 e to the minus I 3 theta over 2. Now you may know that we can write exponentials of negative things in terms of complex numbers, in terms of sines and cosines. Now e to the ix is equal to cosine x plus I sine x, and e to the minus ix is equal to cosine x minus I sine x. So z is going to be equal to k1 over the square root of 2 pi r, because that's r to the minus 1/2. E to the minus I theta over 2 would be the same as writing cosine theta over 2 minus I sine theta over 2. And then z prime here would be, we've got the minus 1/2. We've got k1. We've got square root of 2 pi r. Since it's r to the minus 3/2, we want to leave this common factor here. We'll have another r on the bottom, and then we'll have cosine 3 theta over 2 minus I sine 3 theta over 2. Now the next step we want to do is we want to take the real part of z. So let me pause this and we'll cut this out and move this up. All right, sigma x is the real part of z minus y times the imaginary part of z prime. Well, if we look at the real part of z, it's going to be this stuff. K1 over square root 2 pi r cosine theta over 2. And if we look at y times the imaginary part of z prime, okay, this stuff right here and this stuff is going to be the imaginary part, but we need to multiply it by a y. So y times the imaginary part of z prime is going to be equal to y times k1 over square root 2 pi r times 1 over r times negative 1/2 times minus sine 3 theta over 2. So that leaves us with sigma x being equal to these two parts added together. There's a common factor of k1 over square root of 2 pi r that we can take out. For the first term, we have cosine theta over 2. And on the second term, we have minus y over 2r sine 3 theta over 2. Put a square bracket there. And if we look at our triangle that we had constructed before, where this is r, this is the height y, and this is the angle theta, if we notice here, if we took the sine of theta, that would be equal to y over r. Make a lowercase r. So sigma x is equal to k1 over square root 2 pi r cosine theta over 2 minus 1/2 sine theta sine 3 theta over 2. Now, we're going to use a trig identity. if we have 2 sine alpha cosine alpha, that's equal to sine 2 alpha. So I'm going to write, I'll be able to write sine theta over 2 and another sine theta over 2 will be the same is 1/2 sine theta. So I can actually write this sigma x a little bit differently. K1 over square root of 2 pi r cosine theta over 2 minus sine theta over 2, sine theta over 2, and sine 3 theta over 2. Oops, and I just noticed I wrote this down wrong. This should be a cosine here. And that means that this also should be a cosine in one of these terms. All right, that looks better. Now, one more step then is I can factor out cosine theta over 2 from both of those terms. Okay. And in a similar way, I usually leave this as a homework problem. We can find the stress fields for sigma x and for tau xy. Oops. We'd have 1 plus sine theta, and it's just the theta that's divided by 2. Sine 3 theta over 2. And then the tau xy term, see if I can make that a little bigger. Tau xy term would be equal to K1 over square root of 2 pi r. And this lumps up together as sine theta over 2 cosine theta over 2 cosine 3 theta over 2. And I have to be careful. Some of the books that I've noticed don't have these equations written down properly. Some of them do. And of course, we're still looking at a crack in a biaxial stress field. Now, in general terms, we can write this a little bit differently. Sigma ij is equal to K1 over the square root of 2 pi r, where r is the polar coordinate distance from the crack tip, times some functions Fij of theta. And we do want to still note that we're looking at points near the tip of the crack. We're not going too far away, so x star is much less than a. All right, now here's the significance of what this K1 term represents. For linear elastic fracture mechanics and cracks that obey those conditions under which we can have linear elastic fracture mechanics, all the stress fields will be in this similar form. There will be some functions of theta. The stresses will vary with theta. But the singularity will always be a square root of r singularity. And for notational convenience, we have that square root of 2 pi on the bottom. And the strength of the singularity, however, is determined by that K1. So this K1 is important because it appears in every stress term and is the strength of that singularity. So we know for the problem that we were just looking at, the cracked plate of crack length 2a, that the K1 is equal to sigma square root pi a. For other crack configurations, an edge cracked plate or something like that, we're going to have slightly different ways that we're going to calculate K1, but it's usually always in terms of the remote stress and some sort of crack length parameter. Sometimes it will involve adjustments based on the width of the plate and different things like that. But that K1 is a great number for characterizing the strength of the stress fields, the strength of the singularity for the stress fields around the crack tip. And as such, we can use this as a criterion for failure. So when our value of K1 is greater than or equal to some critical value of K1, then the material would be expected to fracture. In a similar way is in mechanics materials, if we have a uniaxial stress field, if your sigma is greater than your yield strength, then the material yields. Well, in this way, we can use this K1 as a fracture criterion. All right, we'll talk about more of this in class. If you have any questions, please email me. I expect I'll go over all of this in our fracture mechanics class on the board as well.